Hello students, for this particular organic bridging module, I'm going to go through some of the important ideas which you would have already learned in Sec 3 and Sec 4. I do not really need to go a lot into details because quite a bit of it were covered under chemical bonding, and the usual organic functional groups which you learn in secondary school will also be covered in detail in the A-level curriculum. So for this particular bridging, I'm just going to highlight some of the very basic things which you should know before you come over. Okay, so I think the first thing I'm going to highlight would be in terms of the naming of the organic compounds. Okay, so when it comes to naming, just need to highlight to you maybe the most common functional group which we're going to deal with. Okay, so that will be alkanes. Okay, so we're going to deal with alkanes first. So I'm just going to put the alkanes over here. Okay, so in terms of naming, the first 4 carbons, okay, or the first 4 members are the most unusual ones. Okay, so number of carbons, I'm just going to type this out, number of carbons here. Okay, so we'll have 1 carbon, 2, 3, and 4. Okay, so this will be in terms of naming, so 1, 2, 3, and 4. And before I forgot to introduce, alkane is actually what we call a hydrocarbon. It's a hydrocarbon with molecular formula C with a subscript N, and then H 2N plus 2. Okay, 2N plus 2. Okay, so it has this particular formula, and this actually applies to straight chain alkane. Straight chain alkane means that the 2 ends are opened. So I think we will illustrate this in the naming so that is a lot clearer. Okay, so the first member we call it methane. Okay, so you notice that it ends with ANE. Okay, so maybe I'll just highlight the ANE with a different color. So I'll just put blue. So it ends with ANE. So just highlight it blue so it's clearer. Okay, so please remember the prefix, which is meth. Okay, methane, and then this is followed by ethane. So F. Okay, so with 2 carbons. Okay, and then the one with 3 carbons, the prefix with props, so that's propane. Okay, and then the one with 4 carbons will be bute, so butane. Okay, unfortunately you have to remember the way they are being named, at least the common ones, so minimally the first 4 members. And those of you who have been through O-levels, I think in O-levels you are required to remember the naming for the first 4 members. So that's meth, F, prop, and bute. Okay, so I think just 4 names to remember. Some of you might be wondering what about beyond the number 4? Okay, what about 5? Okay, from 5 onwards, it's actually quite easy to predict the name because it kind of like follow the usual convention. So 5 we call it pent, and as most of you know, pent means 5, right? And then what about 6? Okay, so those of you who predicted correctly, you will know that 6 is hex, so we will call it hexane. Okay, and so on and so forth. Okay, so I'm not going to go into details the rest because you can easily find them in the lecture book you have just collected. Okay, then what about the structure? So over here, I'm going to show you the structure. So in terms of the structure, I'm just going to show you the displayed formula. Okay, so you're going to learn in A-levels that displayed formula means it's a formula where all the bonds are clearly shown. Okay, so for methane, usually in a textbook setting, you'll be drawn with a structure that looks like this. So it looks like a square planar structure, but it's actually not square planar. Yeah, so it's actually tetrahedral. Okay, so based on what you have learned in chemical bonding, you will know that it's actually tetrahedral. Okay, so I'm just going to paste this over to the 3D, then you can easily see the 3D structure. Okay, so it's tetrahedral. You can see the tetrahedral carbons here, and the angle is 109.5 degrees. Okay. Later on in H2, you're going to learn to incorporate the 3D projection into your structure drawing. So maybe I can just do a very brief introduction on the 3D projection over here, so that later on when you learn that topic or when you are introduced to that, it's a lot easier. Okay, how do we look at 3D projection? Okay, so if you look at a tetrahedral carbon with 4 hydrogens, so can you actually see that at any one point in time there will be 3 atoms along the same plane? So this H carbon and H they are on the same plane. So it's really up to you to define. If you define the other 2 H and the carbon, it will be like this. So they are on the same plane. Okay, so I'm just going to define it this way. So can you see that when I put the carbon H and H on the same plane, you can see that this particular hydrogen is actually projecting out towards you, and the other one is projecting inwards. Okay, so maybe I rotate it a little bit, you can see. So one is projecting towards you, and the other one is projecting inwards. And this H, this carbon, and this H are on the same plane. Okay, so on paper, which you're going to look at it from your lecture book, you will represent it this way. So the normal carbon, okay, so those on the same plane one will be just represented with a normal bond. Okay, so I'll just put the H in first, and then for the one with the bond with the H projecting towards you, it will be like this, and the one with the H projecting away from you, it will be represented with the hash line. So this is the bow and the hash line. Okay, so this actually represents the structure with a tetrahedral geometry. Okay, so I'll just put them side by side. Yeah, you wouldn't learn this in secondary school. So although I said this is like a bridging, but I thought I just want to introduce you to what you learn or what you would have learned in secondary school, and then maybe just add a little bit more. Yeah, so that later on when you read through your organic booklets, the ideas are more in sync. Okay, yep. And I'm going to move on to ethane. So for ethane, the displayed formula will have a total of 2 carbons. So just going to draw it out. So this carbon here, and then H, H, and H. Okay, so yeah, you will normally see this appearing in textbooks and even notes. Yeah, so this is C2H6. Okay, and if I'm going to put this in the 3D structure, it'll look like this. Okay, I think it's not new. So yeah, you're going to see a ethane. Okay, so those of you who aspire to do H3, you'll learn something called conformation analysis, but we're not going into details here. Yeah, so this is ethane, yeah, with the tetrahedral geometry on the various, carbon, the 2 carbons here. Okay, yep, so I'm going to switch to this. Okay, then I'm going to move on to propane. Okay, so again, nothing very inspiring. I'm just going to elongate the carbon chain, okay, by 1 more carbon here. Yep, so this will be H, H, and H. Okay, so H, H, H. Okay, so I hope you also realize from the formula, why is it CnH2n plus 2? Why is there a plus 2? Yeah, because you realize that for every carbon in the middle, right, there will always be 2H attached to it, except the one at the rear, okay, at the 2 ends. So the one at the 2 end, right, they have an extra, a so-called extra H. So we call this, we just name this extra H, or we just number it as plus 2. So that's why it's CnH2n plus 2. Yep, so these are the extra H's. Okay, yep, and then I'm not going to do for everything. So the last one I'm going to do will be for butane. Okay, so for butane, I'm just going to elongate the structure as well with a carbon here. Okay, and then a H, and a H. Okay, so I'm just going to put a H here, a H here, and a H here. Okay, just going to change the color because it was coded differently earlier on. Yep, so this is butane. So butane will be C4H10. Okay, yep. So so these are the introduction to the hydrocarbons. In this case, alkane, and how do we name alkanes? Okay, all right. Then the next part I'm going to move on would be how do we name alkenes? Okay, so what about alkenes? Okay, so alkene instead of ANE is now ending with ENE. Okay, so that means that there is at least one CC double bond present. Okay, or in the language of organic chemistry, we say that there is at least 1 degree of unsaturation. Okay, you're gonna hear this term occasionally. Yeah, so that's alkene. Okay, so what do we do with alkene? You know that you need at least 2 carbon, okay, to form a CC double bond. Yeah, so the simplest member for an alkene will not be with 1 carbon. Okay, so the simplest member will actually have 2 carbons. Okay, so in that case, for the case of alkene, the first member will be ethene. Okay, and when we draw out the structure, so normally for I mean, in secondary school, you will simply just put a CC double bond in between the two, okay, or rather just put a double bond, okay, and then you'll remove those at the end, okay. So you'll see something like this. But for H2, we would really want all of you to showcase it with the trigonal planar geometry. So like this, yeah. In order, as a reminder that the bond angle is 120. Okay, so yeah, do showcase it with the trigonal planar geometry where possible. Okay, I mean in most cases you can try to do that lah. Okay, so again, ethene will look like this. Then of course the next one will be propene. Okay, so propene again, I'm just going to paste this over to the other side. Okay, so that's easier. Okay, I'm going to change the name, so it will be propene, and then just going to add a double bond, but I'm just going to remove the H first. Okay, so I'm just going to put a double bond between this blue carbon. Okay, yep, and then I'm going to remove one H. Yeah, so then the structure will look sound, will appear sound. Okay, so we'll call this propene. Okay, so propene will have 1 CC double bond, and you will notice that there actually isn't a difference whether I put the CC double bond between this carbon and this carbon or between the other 2 carbon. Yeah, because basically the structure is just flipping it over. Okay, so I'm just going to show you how it looks like. Okay, so whether the CC double bond is between the first 2 carbon or carbon 2 and 3, actually there isn't much of a difference. So these two are actually the same structure. Yep. Okay, yep, so no difference. So I'm just going to remove that. Okay, so the next member will be butene. Okay, so butene is a little bit more interesting, which I'm going to elaborate over here. Yeah, so I'm just going to paste this over. Okay, and in black. Okay, so for butene, if I were to number the carbon from left to right, 1, 2, 3, 4, right, you'll notice that there is a difference where I put a double bond. So if I choose to put a double bond or place the double bond between the first 2 carbon, then it will look a little bit different. from the one if I put it in the middle. Okay, so let me just make it a trigonal planar geometry first. Yeah, so I'm just going to make it a trigonal planar geometry over here. Okay, yeah, so if I put the double bond between the first two carbon, yeah, then it will definitely be different if I'm going to put it in the next two carbon. So I'm just going to paste the structure over. Okay, and then I'm just going to put it here, and then I'm going to erase this two and put a double bond here. Okay, yeah. So you notice there's a difference because when we look at the position of the double bond, as we go from left to right, this is 1, 2, 3, 4. So it's between these two carbon. It's between the first two carbon. So we give it a name. We call it 1-butene. Okay, or we can name it in a slightly different way. We can call it but1-ene. Okay, but1-ene. Okay, the 1 indicates the position of the double bond which it is first bonded to. Okay, so in this case, it's between carbon 1 and 2, but we just give it the one with the lower number. Okay, so that is clear cut. Yeah. So in this case, we will call this 2-butene. Okay, 2-butene. Okay, or we can call it but2-ene. Okay, but2-ene. Yeah. So that depends on the position of the CC double bond. Okay. Yeah. Then from secondary school, your teacher might introduce to you that to tell you that, oh, these two structures are what we call isomers. Okay, isomers. Yeah. So in H2 we will elaborate a little bit more where you encounter different terms. So specifically we call them constitutional isomers, but we'll elaborate that in the H2 lectures. Okay. Yep. And I think if you scrutinize hard enough, you can actually arrange, okay, the carbon such that they are no longer in straight chain. Okay, same case goes for your straight chain butane. Yeah, so for your straight chain butane, if you choose to switch this group over to the middle, then you are actually getting a new compound. So we call that an isomers. Okay, so we call that an isomer. So we good. So I'm just going to illustrate this to you. So if we take this and then I'm just going to, okay, first I think I'm just going to put them the same color. Okay, and then I'm just going to remove this group. Okay, and then I'm just going to put a carbon here. Okay, so this will be carbon, and then H. Okay, so H. Okay, so yeah, so this structure will be an isomer of butane. Why? Why do we call it isomer? Because they share the same molecular formula, but they differ in the positioning of the carbon chain. So in this case, for the straight chain butane, we have all the carbon chain in one line. So 1, 2, 3, 4. But for this case, one of the carbon is now branched into the middle one. Yeah, so it's 1, 2, 3, and then I cannot continue moving to the right without lifting my cursor and put it here. Yeah, so we call this an isomer. Okay, so specifically, we will name this as 2-methyl propane. You're going to learn this in introductory organic chem naming. Okay, so the naming here is not very important, so I don't want to bore you with the details in the naming of all these organic molecules, but yeah, but just to take note that the naming will be slightly different. And then how do we know why is it called 2-methyl propane, etc.? Yeah, so we will discuss more of that when we discuss organic chemistry in H2. Okay, just to let you know the difference. Yeah, so again, with the same idea, we can also shift the group around. So for this, if I just going to show you another possible isomer. Okay, so I can have a carbon here with 3 H's. So 1, 2, 3. So you can have a H here, H, H, and H. Okay, yep. So this will also be an isomer of butene. Okay, it has to be butene because 4 carbon, 1 CC double bond. Okay, but how do we name this? Okay, so this will be the interesting part. Okay, so I'm just going to color code this thing first, so that it will be easier for us to name it. Okay, so I'm going to just color code this in blue. Okay, so you realize that when we name, we'll usually name it after the one with the longest chain. So the longest chain is actually a propene. Okay, it's actually a propene. Yeah, and then we need to indicate where the double bond is. So this is obviously 1 propene, but you don't usually call something 1 propene because propene is so-called propene, right? Yeah, so you just call this propene. And specifically, where is the exact methyl group? So the methyl group is actually in the 2nd position. So we call this 2-methyl propene because the methyl group is in the 2nd position. Okay, so 1, 2, 3. So 2-methyl propene. Yeah. Sometimes students will get a bit confused because they will think that 4 carbon, how come we call this propene? Yeah. Okay, so basically we always name something after the longest chain. Yeah, so with that coming into the picture, I hope it's not that confusing. Although in the beginning it can be quite confusing. Okay, and then in secondary school, your teacher might also have I mean you might also have asked your teacher some stuff like for example, let's say 2-butene, right? If let's say I change the position of one of the CH double bond, let's say instead of a CH3 here, I put it here. So you might ask your teacher whether there is a difference. Okay, so maybe just let me illustrate and then you'll know what I'm talking about. Okay, so instead of having the H, the CH3, now you choose to put it here. So I'm just going to shift this up so that it looks more trigonal. Okay, something like that. Maybe you might have asked your teacher, is there a difference? So back in secondary school, your teacher might say, oh, okay, actually it doesn't really matter. No difference in secondary school. Okay, and then they tell you, don't worry about it. No, whether you draw it this way or this way, actually it doesn't matter. Okay, so I mean the truth is actually it does matter. What you're gonna learn in H2. Yeah, so you will learn that the CC double bond, because of the presence of the pi bond, right? It is not freely rotatable. Yeah, so because it's not freely rotatable, so the two structures are actually you can't interconvert them at room temperature. Yeah, so we call them they are actually different isomers. So we give them a special name. We call them cis-trans isomers. Okay, so as this is a bridging, I'm really not going to go into details, but I'm just going to illustrate to you here since I have talked about it. So I'm just going to put in the carbon, okay, and then and the groups. Okay, so I'm not going to draw this plate, so I'm just going to show you this structure, CH3. Okay, so like this, and then H. Okay, so we call this cis. Okay, so specifically we call it cis but2-in. Okay, and then another structure we'll call it trans. So this will be trans. Yeah, so this is cis and this is trans. Yeah, so if you want to draw an analogy, yeah, the cis structure is analogous to this, but if you draw this in H2, you'll be marked down because remember I said that it needs to be shown to be in a trigonal planar geometry. So for this bridging, for illustration purposes, I did not put them in trigonal planar geometry for everything. Yeah, but for the purpose of H2, there is a need for you to arrange them in a proper way. Okay, can? Yeah, so basically I've introduced all of you to the idea of alkane and alkene. Okay, so again, alkenes are hydrocarbon with molecular formula CnH2n plus 2. Alkenes have the molecular formula CnH2n. Okay, and then when you learn more about H2, you will learn about other kinds of hydrocarbons. For example, cycloalkane. You will also learn about cycloalkene. You will learn about benzene. So we're not going to go into those. Okay, yeah. So the next thing you will have learned in secondary school will be alcohols. So I'm going to shift over here. So it will be alcohols. So alcohols. So AlCOHOL. Okay. Yeah. So alcohols have many types, but the focus is actually on the alcohol functional group, which is what we call the OH functional group. Okay, and of course the smallest member will be one carbon, like methanol. Yeah, so you realize that the naming is actually quite boring. So if I were to go back here, I can simply just paste everything over. Okay, I just paste everything over here. Okay, and then I'm just going to change the name. So the simplest member will be methanol. OL. Just change the OL. Okay, and then after that, ethanol. OL. And then propanol. OL. And then butanol. OL. And that's it. Okay. And what about the structure formula? Okay, so it's the same thing. I'm just going to paste everything over. So just going to paste everything over to the right. Okay, and then but of course I will delete this. So again, we're going to put an OH right at the end. Yeah, then for those of you who are sharp enough, I'm not drawing them to show any form of geometry. So normally it's drawn like that. You might mistakenly think that the bond angle is actually 180, but it's not. It's actually 104.5. Okay, it's because there's two lone pair on it. Okay, yeah. Okay, I'm going to just change everything to black. Okay, and then I'm going to draw an OH. So ethanol is the OH is right at the end. Okay, so this will be ethanol. Okay, and then of course for propanol, the OH is right at the end as well. Okay, but those of you who are sharp enough, you realize that from propanol onwards, I can sort of decide where the position of OH is. Because for ethanol, whether is it here or is it at the other side, if I just flip it, okay, it's actually the same thing because the OH is on the first carbon. Okay, so these are the same thing. Yep, same as propanol. But for propanol, if I put the OH right in the middle, okay, it's actually different. Yep, so that is where isomers exist. Isomerization exists. So this is called 1-propanol and this is called 2-propanol. Okay, so that's the difference. Yeah. Yeah, so again, they have slightly different property. Yeah, so if you go into the chapter of alcohols, you'll learn that 1-propanol is actually a primary alcohol, and then 2-propanol is what we call secondary alcohol in H2 chemistry lingos, but we're not going to go into that today. Okay, and then of course, for butanol, it's definitely going to get a lot more complicated because the OH can be found in the first carbon. Okay, it can also be found on the second carbon. So if I'm just going to erase this, it can be found on the second carbon. So going to have a O and a H. Okay, so it can be found here. Okay, and then at the same time, we can also do some branching for isomerization to occur. Okay, so for example, in this case, I can actually shift one of the CH3 to the middle. So if I'm going to shift the CH3 right into the middle, you're going to end up with something like this. Okay, so I'm just going to draw out the H's for illustration purposes, but in most cases, you actually don't have to draw all the H's, okay? Yeah. Okay, so you can see that now I have a branch group over here. Okay, but this still remains as a primary alcohol. Okay, then for 2-butanol, I can also do another branching. Okay, so now I can branch it like this. Okay, I can put my H here, and then I can put my CH3 here as well. So I'm just going to illustrate like this, H, and then a carbon. Yeah, and then you notice that this will become a tertiary alcohol in the lingos of H2 organic chem, but again, I'm not going to go into details. Why is it called tertiary? Okay, those of you who are interested, you can read more about it. Yeah, so you realize that as the carbon chain increases, you are able to actually draw more and more different kinds of isomers, and then things will get a little bit complicated. Of course, for alcohols, it's not just limited to this. Later on, you're going to learn about stereoisomers. So just now, our cis-trans over here is actually some form of stereoisomerism, which we call cis-trans isomerism. Yeah, because the only difference between the two structures is in terms of the projection of the groups in space. Yeah, and then for H2, you're going to learn that 2-butanol displays stereoisomerism as well. In this case, we call it enantiomerism because there is a chiral center. Yeah, but again, I'm not going to go into that because that's not the purpose of the bridging module, but just to introduce that that these are the possible things that could happen. Okay, that you will learn. In fact, if you just read the first chapter in your introductory organic chemistry, you will have encountered the term enantiomerism as well as cis-trans isomerism. Okay, so these are the alcohols family. Okay, so moving to the next group, to the next functional group, which is probably the final functional group you will learn in secondary school. We call it carboxylic acids. Okay, carboxylic acid. Okay, so for carboxylic acid, again, it is possible for you to have all the 4 members. Some students find it a bit surprising, but actually it's not very surprising. So again, I'm just going to paste this over to the right. Okay, so that we can just draw them out. Okay, yeah. Okay, so carboxylic acids. Yeah, but the naming is slightly okay. It's actually not as complicated. So the first member will be called metanoic acid. So again, just replace it. Okay, metanoic acid. And then after that, the second member will be called ethanoic acid. Okay, and this is followed by propanoic acid, and then the fourth member, butanoic acid. Okay, yep. And then how do they look like? Okay, so so carboxylic acid is a functional group itself. Okay, it's a functional group itself. So and the functional group has the abbreviation COOH. Yes, so therefore for the first member, that carbon itself is the functional group. So again, just going to replace it with a double bond here, and then an oxygen. Yeah, so metanoic acid structure formula is like this. So of course, it's supposed to be trigonal planar geometry and then bands, but again, we're not so particular about it in this bridging course, so we just draw it out in the kind of representation you would expect from any O-level or secondary school text or notes. Okay, so this is HCO2H. So a better way to represent it will be like this. We call this the condensed structure formula, HCO2H. But of course, I'm not going to bore you with the details. yeah, so those details will be included in the notes, and of course in the future videos. Yeah, so we call this HCO2H methanoic acid. Okay, then again for ethanoic acid, so again we're going to replace it, and then with double bonded oxygen. So yeah, so double bonded oxygen. Okay, so this is called ethanoic acid. Ethanoic acid is found in vinegar. Okay, so vinegar is about 5% ethanoic acid, so it has that characteristic sour kind of smell. Okay, so those of you who don't like it, yeah, yeah, you know how it smells like. Okay, so that's ethanoic acid. Okay, then next will be propanoic acid. Replace it with COH, and then finally we have butanoic acid. Okay, yeah. So is it possible to have isomers? Yes, same thing. So again, if we replace this CH3 with the H here, so we swap position, yeah, so you get an isomer. But I'm not going to attempt to draw them out now because it's not necessary. Okay, yeah, yeah. So these are the carboxylic acid. Okay, so in short, I'm just going to zoom up a little bit. Okay, so in short, in secondary school, you have learned four major functional groups. Okay, one is alkane. Okay, one is alkene with a CC double bond. Okay, so the usual misconception students have on alkene is that there can only be one CC double bond. That is not correct. Yeah, so if I go on to more than 3 carbon, in fact, I can have multiple double bond. Yeah, but what we are showcasing here is just the simplest family, like we start with alkane, and then we move on to ethane, and then propane, and then for alkene, we start with ethene with 1 CC double bond, propane with 2 CC double bond, and then propane with 1 CC double bond, and then butane with 1 CC double bond, but we elongate the carbon chain. Okay, and then earlier on, I also showcased to you where it's possible for you to have isomers, where even for butane, you can have you can swap one of the groups, okay, in the middle, and we call this 2-methylpropane. And then butane, you can have a lot more isomers. And then I briefly introduced you to cis-trans isomers, where they differ in their projection in space between the cis isomer and the trans isomer. And then after that, I move on to alcohols, where I show you that the naming is similar from methanol all the way to butanol, and then the position of the OH, and then the position of OH can also vary for 3 carbon and above. Okay. Also, let me highlight that I did not showcase any members above 4 carbon. That doesn't mean they don't exist. Actually, they do exist, and in most cases really exist. However, I just need to show you the basics, so I don't have to show you everything beyond that, and you can easily pick them up when you read through the introductory organic chemistry notes. Okay, so next will be carboxylic acids. So carboxylic acid, simplest member is methanoic acid, and then ethanoic acid, propanoic acid, butanoic acid. Isomers also exist, okay, for butanoic acid and above. Okay, and then finally, I'm going to introduce to you a little bit about the little kind of reaction that you might have learned before in secondary school, which is really related to all these functional groups. Okay, so I think the first reaction I thought I just want to introduce you would be an addition reaction. Okay, so what exactly is an addition reaction? So for the case of, let's say butene, okay, so if I simply subject it to hydrogen gas, okay, right? Yeah, then you expect the hydrogen gas to add across the double bond so that your butene will become butane. Okay, so that's what we call an addition reaction. So you become butane that looks something like this. Okay, so in secondary school, you have learned it as an addition reaction. Okay, so in case you vaguely have some memory about it, that's good. Yeah, so this addition reaction is a quite characteristic of unsaturated compounds like butene, like alkenes, those with CC double bonds or even triple bonds, etc. Yeah, so we call this addition reaction. But some of you, you might also realize that it can't happen the way I wrote it, because you need a catalyst. So platinum surface is a good catalyst, or even nickel. Yeah, and because a catalyst is needed, sometimes we call this catalytic addition. Yeah, because catalyst is needed. Yeah, and because we are using hydrogen gas, some of you might learn it in secondary school, and this reaction might be called catalytic hydrogenation or catalytic reduction. So they mean similar things. Okay, so that's something that I hope it will help you to refresh your memory. Okay, and then another very important reaction which I thought I should make mention is actually the reaction between alcohols and acids. Okay, because they form a new functional group that is quite important in H2 chemistry. Okay, so I'm going to use ethanol as an example. Okay, I'm just going to shift it down here. I'm going to use ethanol as an example, and then I will use maybe propanoic acid. Okay, okay, I will use this as an example, and I will flip my ethanol to make discussion easier. Okay, yeah. So when these two react, so I'm going to just color code this. Okay, uh, they are going to form a new functional group known as an ester. Okay, so the H, so they will lose a H2O out. Okay, so I'm going to draw the new compound for you. So when they react, usually under suitable condition lah. I mean, they don't just react like this. Okay, so I'm not going to go into the condition. If you remember in secondary school, you will have learned this as condensation reaction. Okay, condensation. You might need corn sulfuric acid, but again, those are not important at this stage. Okay, so I'm going to draw for you. So this portion, I'll keep it as black. Okay, and then the other portion, maybe I will use blue. Okay, just going to switch over. Yeah, and then you form a new bond between the O, the O from the alcohol and the C from the carboxylic acid. Yeah, so this new functional group is known as an ester functional group. Okay, so I'm going to spell it out. Ester. Okay, so you're going to form a new ester functional group. And then, of course, H2O is the byproduct. Okay, H2O is a byproduct. There's a difference between side product and byproducts. If you don't know the difference, maybe you can go and think about it. Okay, that is a huge difference. But yeah, so we can discuss this more in the tutorials. Okay, so the fourth reaction is called condensation, or secondary school, some of you might remember your teacher telling you it's called esterification. Yeah, so yeah, you might want to refresh your memory a little bit. Okay, the reverse, it is possible to go reversed. Yeah, so the reverse reaction, because it involves water, yeah, is known as hydrolysis. Yeah, so those of you who took bio, this term might be a bit meaningful to you lah, because hydro means you use water, lysis means you use water to break up something. So lysis means break, so use water to break up something. So in this case, we are breaking up the ester linkage or the ester functional group. So this is actually the ester functional group. Yeah. Okay, so I guess that's about it. There isn't much other things I thought I could highlight over here, because any other things I thought we could always discuss in the tutorial, or even in the setting, in the lecture kind of setting for the H2 organic chemistry bits. Yeah, so I I hope you'll find this bridging portion interesting, or I mean maybe not interesting, but useful for your learning. And then I mean hopefully uh, your journey into organic chemistry is not as difficult as it seems.